Right. So let's continue with this example 6.3. Obtain the RTL design that realize the following computation blocks. Right. So we have two equations, x equal to e multiply a plus b plus c, and y equal to a plus c multiplied by c plus d. So how to obtain the RTL design for this, such that we can create the hardware later on. Okay, so remember, if we want to create the design, means that we need to create the data path and also the controller unit for the design. What we need to do is, let's look at this. Design the data paths that allow for concurrent computation of three addition. Do not perform code restructuring. This means x is realized as this. Okay, so meaning that in this question, number one, it is not allowed um, to modify the equation. So we need to create the RTL design based on exactly for this equation. So the code restructuring is not allowed. So first step is to have the DFG, right? So let's have the DFG for the design. So we have E equal to x equal to a plus b plus c, and also y equal to a plus c multiplied by c plus d. Okay. All right. So this is what we have, the equation, or we can call it the algorithm, right? In the form of equation. So first step is to create the DFG, right? DFG, yeah. So to create the DFG, we can this is can be done by, yeah, straightforward. We have a plus b, so we can have the plus. We can have a plus b for this, and we can have another one plus c to get the whole terms here. Okay, so this is again add, and we can add we can multiply by e, right? Multiply everything with by e, so we can have the multiplier, we have e, and we can have x at the output, and we have another one, a plus c. Okay, so that a is actually the same a as this one. So maybe I write here a plus c. So this a and this a is the same, yeah. A plus c, and I have c plus d, and we have multiplication here, multiply, to get y. Okay, so this will be our DFG. And from DFG, we need to do the resource allocation and also the scheduling, right? And this is a very important step, where to do the scheduling, we need to have the cycle, right? The clock cycle. So let's, for example, this will represent the cycle number 1, and this will be the next one. Okay, let's, for example, this is S0, this is S1, this is S2. Okay, so how to allocate this? So we can actually we can use dot to represent a register. We call it art1 here, where we have A stored in art1, because our data must be in the register. So we store our A in art1, and we have our B in art2, and we have this our C in R3, and we have D in R4, and E, because E can be loaded later on, because it's happened at very late state of the design. So maybe we can reutilize the register R1, R2, R3, R4. Yeah, we don't want to put E in R5 just yet, right? It is possible to do that, but we try to reduce the number of register that we want to use in our design. So let's put E in the register later on, right? So let's see, can be done or not. And we have A plus B here. Yeah, this part. This part, right? So we can have here plus A plus B, and the result of this operation we need to keep in the register. So now here B, we need to see whether we want to use B again or not, or A again or not, right? So A again we need to use, but this one can be done in the same cycle, right? A plus, is it A plus C? Yes, A plus C we can have in the same cycle. So this A plus C we can have here, and the result is here. And this one can be saved in R1, all right? R1, and C, because C is needed here in the next operation, so R3 we need to preserve. So this operation we can use R2, because R2 is B, right? And B we only use one time here, So R2 is now available for S1. So we can use to store the result of this operation. So we can use R2, right? And look at this, A plus C we can do in this cycle also. A plus D done, right? The last one is C plus D. Yes, this one is C plus D. This is C plus D. And we have the result here. And we can save in R4, right? And R3, we still need the content of R3 to be brought here to the next clock cycle, R3. Because R3, we still need to add with this result, this operation, right? This one need to add with R3 here. So we need to add this to this, add, yeah, this is A plus B, this is A plus B plus C, and we have the value here. We can use R1 to store the result of this, and the last operation will be this. Add with E, right? Not add, multiply with E, then we get the result in R1 is the X. Okay, and let's check. We have A plus B plus C, and multiply with E, we have X, right? And E, of course, we need the register to store this E. So now R3 is available because we don't need to use R3 anymore after this. So we can use R3 to have E. R3 to have E here. And we need to have this, right? One more operation, which is multiplication. So this multiply with this, we have Y here, and we can use R2 to store the result. All right, so this is the resource allocation and also the schedule that we can have, right? So whether you want to use which register, it actually depend on you, right? In this case, I use R1 here, and also after I add this value A in R1 with B in R2 here, I save the result of this process in R1. You can use R2, right? No problem. Here you can use R1, no problem. All right, but make sure that you not replace the value of the one that you need to use later on. So for example, in this case, because C in R3, we don't want to use R3 in this operation and this operation and this operation, because C we still need in S2, all right, because we want to add C with the result of this. That is why R3 is not written to, all right, there is no value written to R3. So R3 still remain R3 here. So we have R3 plus with R1, we have the value here. Result is saved in R1, and we have E to R3 because R3 now available. We don't want to use R3 anymore, so you can put E in R3, and you do this operation, you get X at the end here. Same as this one for Y. Look at Y. Y you have A plus C, and you have C plus D, and this multiplied by this, you save in R2, right? See, and you can see that here in each register, yeah, there is no variable, or no, there is no data, same data or different data writing into the same register. Here, this one is R1, R2, R3, R4. There is no 2 R1, no duplicate register. R1, R2, R3, R4, R1, R3, R2, R1. All right, so you are safe to do that. Okay, so this is the possible solution, possible allocation, possible schedule, and this is based on what the equation one, because you can have concurrent computation of 3 addition. So you can have up to 3 addition at the same cycle, right? So this is the 3 cycle, 3 addition at the same cycle, means that you need to have 3 adders, right, to do the operation. Okay, so from this, now you can derive the RTL code. Okay, so for example, at S0, here S0, so you can see that you have this, where the RTL code that represent the first operation is to load A into R1, right? So you can have R1 A. So that is the first RTL notation, RTL code that we can write from this. And the next one is R2. You can have R2. You load B into R2. R3. You load C into R3. And the last one, you have R4, where you load D into R4. Right? That is the RTL code for S0. What about S1? S1, you can see here, this is the first one, R1, where you can have R1 is equal to R1 plus R2, right? The operation is R1 is actually R1 plus R2. Okay. Next, you have R2 is actually R1 plus R3. And you have R4 is R3 plus R4. Okay, so that is the RTL operation for the S1. What about S2? S2, first, you can see that you have R3, E, you load E into R3. And the next one, you have R1 equal to R1 plus, this is R3. And you have R2 is R2 multiply R4. Okay, so that is the code for the S2. And the last one, you have R1 is equal to R1 multiplied by R3. Done. All right, now you have the RTL code for this schedule and allocation, or for this design. Okay, and from RTL code, definitely we can derive the data path circuit. All right, so how to do that? We need to look at the RTL code. So from the RTL code, so maybe I need to have this in this new page. Okay, so I have the RTL code here. Now I want to, so I need the cycle as well as a reference. So this is S0, this is S1, this is S2, this is S3, right? So how to create the data path, a circuit from the RTL code, right? Do you know how to do that? So one of your tutorial question, right, from chapter 5, I think Dr. Chua asked you to do the as your assignment, right, to 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 derive the data path unit from the RTL code. So that is about how to derive the data path unit from the RTL code. So now I will show you how, yeah, if you have the RTL code, now how to derive the data path circuit. Okay, and of course the RTL code is from our schedule and the allocation. So here we need to look at the hardware resources that we need to have. First thing first is how many register that we have in our RTL code. How many? We have R1, R2, R3, R4. So we have 4 registers. So we can draw that 4 registers like this. One register, you have another one, you have another one, and another one. This is R1, this is R2, this is R3, this is R4. Okay, now how it is connected, and it is used to connect to what circuit? So you need to have this, an adder, and also the multiplier. So you have two processing or arithmetic circuit, which are the adder and also the multiplier. But the question is how many adders that you need to have. So look at the maximum number of adder or multiplier in each cycle. So we can see here you need 3 adders here, and you don't have multiplier. Here you need 1 adder, and you have 1 multiplier. Here you have one multiplier. All right. So you can see that the maximum number of adders should be 3, number of adders, and the maximum number of multiplier should be equal to 1, and look at the maximum one. All right, so you need to have 3 adders at least in order to perform this operation, right? So let's say, for example, because we have 3 adders, we need to label it clearly. For example, this one we use adder number 1, this operation. This operation is adder number 2. This operation is adder number 3. And this adder can use number 1 or number 2 or number 3, but in this case, let's use number 1. All right, because you have 3 adders, so you can use any of them. And the multiplier, you only have one multiplier, so that doesn't matter to use which one because you have only one. Now you will have 3 adders. So let's say, for example, this is your multiplier, this is your adder, another one, and another one, right? So you will have adder number 1, adder number 2, adder number 3, and let's label this as, this is adder number 1, adder number 2, adder number 3, such that it represents this number 1, number 2, number 3. All right, now we want to connect this. How is this connected to each other? How R1 is connected to the multiplier, how R2 is connected to adder, and so on. Again, we need to look at the RTL code, right? So look at the RTL code. First, look at R1. R1, we have A, the input. Yeah, the input to the R1, we have A. Also, we have from adder number 1. And also we have from, again, adder number 1. This is the same. So this one and this one is the same because this is from adder number 1. Yeah, this is adder number 1. This is also from adder number 1. But this one is from the multiplier. All right, from the multiplier. So we can see that if we have a register R1, and we have 4 input, and only at one time only one input is allowed to enter the register. So what should we do? So we should have a multiplexer, right? We should have a multiplexer where we have A, we have the result from the adder, and the result from the multiplier, right? And of course, we need to have the control signal here. Okay, so that is what we need to have. So in this case, a multiplexer, I don't want to draw like this because it will make the circuit too complicated. So what I want to do is I draw just one line, yeah, to represent my multiplexer. Maybe I have a more vertical line. Okay, so this will represent my multiplexer. Here to to go to R1. So the first one is from the outside, which is A, the input, and the next one is from the multiplier. So it should be from this. The output from the multiplier is from this, right? So it will be here, and another one is from the adder number 1. So I can have something like this. Yeah, and this is a 4-to-1 multiplexer where the last input is not utilized, yeah, because I have only 3 inputs here, right? So it is actually a 4-to-1 multiplexer, and I have the connection now from the multiplier and from the adder to the input of R1. So this should be the input of R1, right? What about R2? So next, again, we need to go to R2 and see what is the input or connection of R2. So we have B to R2. We have the output of the second adder to R2, and we also have the output of multiplier to R2. So again, R2 we have actually 3 input also. First one is from B. Second one is from the second adder. So I can have make it more smaller here. The second adder is from here. And it's for this. And the last one is from the multiplier, right? This one, multiplier. So multiplier, we can see that we have the line for the multiplier already, which is this one. This is multiplier. So we can have the connection from here to here, right? Now you can have the multiplier from here to here. And that is for R2. What about R3? So again, we need to look at this is R3, E, C, and E, and there is no others. So this is easy, where we can have a multiplexer also, but this is 2-to-1 multiplexer because we have only two input, right? One is from C, another one is from E. Okay, that's it for R3. And the last one is R4. R4 we can have this and this from adder number 3 and also D. So we can have multiplexer also. Multiplexer. We can have this is D, and the last one is from this, right? Adder number 3. So we have that for the input for the R1, R2, R3, R4. Okay, So that is for the register. Now what about the multiplier and the adders that we have? So we need to go back to our RTL code again, right? So for example, the multiplier here. What are the inputs to the multiplier? So first we need to look at this. Multiplier, where is multiplier? Yeah, this is the one, and also this is the one. We can see that the first one, yeah, for this one, we have R2 multiplied by R4. And this one, R1 multiplied by R3. Okay, so we can see that because a multiplier, we can only have two input, A and B, for example, right? A and B, two input. But here, the input can be R2 and R1. And for the other one, we can have R2, R4 or R3. Means that at one input of the multiplexer, we need to, or we have two data sources, right? R1, R2 or R4, R3. So we need to have a multiplexer as well, right? In order to handle that. So again, let's have a multiplexer to do that. We have two multiplexer here, 2 to 1 multiplexer, a 2 to 1 multiplexer. One is here, another one is here. Okay, and we have R1, R2. So here can be R1 or R2. And another one is R4 or R3. So we have R3 or R4. Like this, such that we can have or we can perform this operation. So if you want to perform R2 multiplied by R4, for example, so we set this select to select this signal and this select to select this signal to the multiplier. And if we want to perform R2 multiplied by R1 multiplied by R3, so we select this one and this one, then we can perform that operation, right? So that is why we need a multiplexer. And what about the input for the first adder? So we need to go back to our RTL code as well and see where is our first adder, adder number one, this one and this one. Again, we have two equations here. First is R1 plus R2. Second one is R1 plus R3. So for this is the same R1, no problem. So we can have direct connection from R1 to here. But the second one, we have R2 and R3. So again, we need a multiplexer. So here you need a multiplexer, and it is from either R2 or R3, right? So that is for adder number one. What about adder number two? So adder number two is easy because you have only this, yeah. So R1 plus R3. R1. So we look at where is R1. So here is R1. So we can have the wire connected from that, and R1 plus R3. So you can have R3 here. Done. What about adder number 3? Adder number 3 also easy. You have R3 plus R4 only. So you can have R3 plus with your R4. Done. Right? So this will be your data path you need. So the data path will be derived from the RTL code. Right? So you need to have RTL code before you can derive the data path. And to have the RTL code, you need to have the scheduling and allocation. And the scheduling and allocation is derived from the DFG. And the DFG is derived from the algorithm or the equation. Right? So now we have the data path circuit. Okay, so this is the same as the one that we have. So this is the data path circuit. Okay, next I will show you how to design the control unit for this data path to perform this operation. Okay, so although the question not ask you to design the control unit, but I want to show this because later on you need to do for your assignment. So next, how to derive the control unit then? Yeah, to control this data path such that it can perform this operation. Okay, so to do that, you need to have the what we call the RTLCS table, yeah, the control sequence table, right? So you can have the control sequence table, but before you do that, you need to have the label. Yeah, you need to label your data path such that you can have the correct control signals, yeah, in order to derive your CS table. So first thing that you need to have is that you need to label what are the control signal that you need in this case. So here, of course, the register, you need to have the load signal, yeah, to load the data from the input. So let's name this as LD1, this as LD1, this LD2 for, to load the signal to this, LD3, LD4, right? And for the multiplexer, you need a control signal, right? So the control signal for this, let's name it this as SEL R1, and this is 2-bit, right? Because you have 4-to-1 multiplexer. Name this one as SEL R2, 2-bit also. This is SEL R3, 1-bit, because this is 2-to-1 multiplexer. SEL R4 for this one. And you have another multiplexer here for the multiplier. Let's name this as SEL M1, this one as SEL M2, and the last one here is SELA. And all of these multiplexer are the 2-to-1 multiplexer. Right? So that is how we have this. Any other signals that we need to have? No, right? This is enough. Now we need to create the CS table. So let's create the CS table for this. You can write on paper, or you can use maybe Excel, such that it's easier for you to keep track. Okay, so let's have this, where we can have this. We have RTL code. Okay, and we can have LD1, we can have LD2, LD3, LD4, we can have SEL R1, bit number 1, we have SEL R1, bit number 0, and here we can have RTL R2, and this is also R2, 2-bit also, and we have SEL R3, we have SEL R4, we have SEL M1, SEL M2, and we have SEL A. Okay, so how many bits that we need to have? The control signal: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So we need to have 13 control signal. So this means that if we draw the control unit, our control unit will look something like this. Okay, so if we draw the controller, which is actually the finite state machine, FSM. So you will have the state register, and you will have the output logic and also the input logic, right? And this is D flip-flops. You have a clock, and this is output logic. This is the next state logic, right? And you have this input to this input, and the output here will be the one that will be the control unit, which is LD1, LD2, LD3, LD4, until the number 13 one, which is the SELA. All right, all are 13 bit. Okay, and again, the more type FSM, you have the feedback from this to this. Now my question is, what is the size of your finite state machine, or your register? What is the size of the register? How many bits? So based on this, we have how many states? We have 4 states. S0, S1, S2, S3, 4 states. So if you have 4 states, this must be at least 2 bits, all right, to represent 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so this will be our control circuit, and our task is to create this logic, all right, based on its behavior, right? As in S0, what we need to have is we need to do this operation. So to do that, what we need to do is to activate the control signal at the correct time, right? So in S0, we have R1 A, we have R2 B, we have R3 C, and we have R4 D, right? So to do this, to load R1 to A to R1, B to R1, R2, C to R3, and D to R4, definitely the signal that we need to activate is this LD1 must be 1, right? LD2 must be 1, LD3 must be 1, LD4 must be 1 in order to load all the signal, all the data to the register. And what about this? This is very important also. So based on how we have the circuit here. So let's, for example, in this multiplexer, yeah, if in this multiplexer, if for example, if we have 0, 0, yeah, SELR1 equal to 0, 0, so we will select A. If it is 0, 1, we will select this line, which is the multiplier. If 1, 0 or number 2, we will select this line, which is the adder, number 1. So same as this one, 0, 1, 2. This is 0, 1. This is 0, 1. This is 0, 1, 0, 1, 0, 1. So let's have something like that, such that when we want to select A into R1, so this SEL R1 must be 0, 0, right? So we have 0, 0. And to select B to R2, so this should be 0, 0 also. SEL S2 R2 must be 0, 0. So we have 0, 0. SEL3, SELR3, because we want C, so it is must be 1. So we have 1 here. This one R4, because we want to select D, so it is 1. SEL M1, M2, SEL A, actually we don't care about that, so make it 0. So that is the signal that we need to activate at S0, such that this operation can be done. So we have the first one, Now look at the second or S1 state. All right. So what we need to have? We have R1, R1 plus R2, right? And this is by using adder number 1. We need to label that. We have R2, R1 plus R3. This is adder number 2. And we have R4, R3 plus R4. This is adder number 3, right? Now, for this state, what is the signal that we need to activate? So look at LD1 first. LD1, because we want to write to R1, of course, it need to be 1. LD2, we want to write to R2, so of course, need to be 1. LD3, no, we don't want to write to LD3, so make it 0. LD4, we want to write to R4, so make it 1. Okay, now R1, SEL R1. So what is the signal that we need to have here? So because we want the data is from the adder, so we need to go to here and look at the data that is from the adder is this. So it must, oh no, this one is this. So it must be number 2 or 1 0 for this. So this is 1, this is 0, right? What about this? R2. So R2, yeah, we have from the adder number 2. So what is adder number 2? This is adder number 2. So the line is here. So it is must be 0 1, right? So you will have 0 1. SEL R3? No. You don't want to use any R3, not writing anything to R3. So you don't have to have. So this is 0. SEL R4? Yes, because you have this. So it is from this. So it should be 0. Should be 0, right? Should be 0. SEL M1. M1, this, whether we want to use which one, 1 or 0. So it depends on what we do. So in this case, we want to, yeah, this one is R1 plus R2, 2. So R1, we need to look at this, or this is R1. And this is R1 plus R2, right? Okay, so we want to do R1 plus R2. So here we need R2 and this is multiplier. So this is the one. So R1 plus R2 is this one. R1, no problem. SELA, R2 should be 1. So SELA should be 1. Multiplier, do we use multiplier? No, we don't use multiplier, so this should be 0 and 0. And what about the other? This, nothing to do, right? So that should be our control signal. So that will be for S1. What about S2? So maybe I can copy this, right? And just delete this one. And we have S2. So S2 is the R1, R1 plus R3, and this will be adder number 1. R2, R2 multiply R4 by R4, and we have the last one, R3 is loaded with E. Okay, so let's see what are the signals that we need to activate. First, we want to write to R1, LD1 must be 1. We want to write to R2, must be 1. We want to write to R3, must be 1. R4, no need to write anything into it, so must be 0. And here, we want the to R1, so it should be these two signals, the SEL R1 for the multiplexer for this one, So we want now is from the adder number 1. So from this adder number 1, so it should be 1 0, right? 1 0, same thing. And next is this. This one is R2. Do we want to write anything to R2? Yes, R2 is from the multiplier. So we need to look at the multiplier here. Multiplier to R2, which is this 1 0. So we should have 1 0. SEL R3, yes, we want E, so it should be 0. SEL R4, we don't want to write anything into R4, so make it 0. M, SEL M1, M2, this is important because we want to have this operation R2 multiplied by R4. So here must be, look at the line, we have R4, so we need to have 1 here. So we can have 1 here. And this one should be R2. So what is R2? This one is R2. So it should be 0. And what about select A? Select A is here. We don't want to use anything for this. We used here. So R1 plus R3. R1 plus R3. Where is R3? So this one. So it should be 0, SELA. Should be 0. All right. Now we have the last one. And I should copy this. And this is S3. And let's have a look at the equation. So S3, we have R1 multiply by R3. That's it. So we have only one RTL operation here. So R1, again, this must be 1. The rest should be 0 because we only write to R1. And to R1, this one is very important. So look at this. From the multiplier to R1, so must be 0, 1. So we have 0, 1. Here we don't use. Here we don't use. Also here don't use. But these two should be very important, which is R1 multiplied by R3. So R1 is done, but multiplied by R3, SELA must be R3 must be 0. No, multiply, not this one. Multiply must be this one. Again, R1, M1, multiply. We want to multiply R1 with R3. So here should be R3. So this is R3 should be 0. SEM M0 should be 0. And R1 should be, should be 1 here. Then we have 1. So this is the information that we need in order to design our controller later on. But the controller circuit is actually in the form of this already. Yeah, we have drawn this. So this is the controller, the CU. This is the DU. And DU, although we have this, but we need the CS table. Yeah, this table in order to write the Verilog code later on. Yeah, because we need all the output information for every state that we have here in order to perform that operation. Right? So now we have the data path and also we have the control unit. Now our task is to write the Verilog code. Okay, have create a new project. Let's do this first. So let's have this (6.3) and let's name this as we have 6.3 and we have this one is for DU data path for 6.3 maybe. Okay, because we need to create another one which is the CU, and let's name our project as this. Okay, so what we need is the circuit such that we can write the code. So this is the circuit, and let's have a new file. Okay, so I need only this area, and I need this such that I can describe. Yeah, we need this one. Okay, let's write the code module, and this is the name of our design, and we have the the port that we need to have. Of course, we need a clock because in the register, although we don't have this, we don't have label in this here, CLK, RST, all right, but this is common that the register we need a clock and also the reset, right? And we have the LD1, we have the LD2, LD3, LD4, LD5. No, we don't have LD5. And we have SEL R1. We have SEL R2. We have SEL R3. We have SEL R4. We have SEL M1, SEL M2, and the last one is SEL A. Okay, and maybe we need to have the output, or we can have the register as the output. Okay, so this one should be okay now. And we have the input, and all of this input we need the register R1, R2, R3 as the output as well, such that we can observe the content of register later on. So let's make this as output as well. And again, we forgot the input A, B, C, and D, right? So now the 1-bit input is this until this, except this. These two is not 1-bit, are not 1-bit. Right, there are others 1-bit. We have the 2-bit input, which is these two. These two are 2-bit. We have let's say A, B, C are 8-bit. Yeah, for the data. A, B, C, D, and E. Right, we have E, and of course here we need to have E. All are 8-bit. And we have the output, and it should be in the form of rect 8-bit, R1, R2, R3, R4. Okay, that will be our declaration. And now we want to describe all of the components that we have here. Okay, so first will be this R1 with the multiplexer here. So we can have we call it R1, So we can use sequential block. Clock, we use positive edge clock, and also positive reset. So if reset, what happened to the output? Should be 0, right? When reset. And remember, when you want to describe a sequential circuit, you should use the non-blocking assignment. So this is non-blocking assignment, right? But if not reset, so we will look at another signal, which is the LD1. Look at LD1 here. And again, else, this should be else. If LD1 equal to 1, if LD1 equal to 1, what we need to look at is this, SEL. So it will depend again on SEL-R1. So because SEL-R1, you have 4 possibilities, right? 4 to 1 multiplexer. So you can use case statement, case SEL-R1. So this is 2-bit. If 0, 0, what happened? If 0, 0, you need to have this. If 0, 0 means that you have to have A. Yeah, R1 is equal to A. Else, if you have 0, 1, R1 is, if 0, 1 must be this line, multiplexer. So the output of this multiplexer, we haven't named it yet. So here, we need to give it a name. So let's say we call it mul out, multiplier out, MULOUT. This is add 1, this is, or just MUL, add 2, this is add 3, and we need to declare this as a rect. So rect 720, you have MUL, you have ADD1, you have ADD2, you have ADD3, right? Such that here you can say that if 0, 1 here, 0, 1, so it is actually MUL. So you can have MUL here. But if it is 1, 0, R1 must be 1, 0 is this, so must be ADD 1, and for others, R1 is don't care, right? And this don't care is 8-bit. And case done for the first register R1. Now we describe R2. So to describe R2, and we can see that R2 we have 4 to 1 multiplexer as well here. So actually you can just copy this because the structure must be the same. Right? So just copy this, and here you can say that you have R2, and yeah, post is clock, post is reset. But if reset R2 is now equal to 0, and we use LD2 here, and also we use SEL R2 here, and also the output all are R2. And this is surely different. If 0 0, so the input will be B, and if 0 1 must be this one. 0 1 is add 2, so this one must be add 2. And if 1 0, 1 0 is this one must be MUL, so this must be MUL. And done. For the second register, see, this is easy to describe this and this. And now register number 3 and number 4. Number 3 and number 4 is a little bit different because we have only 2 to 1 multiplexer instead of 4 to 1 like this. But the concept here should be the same. So we can have this and name it R3. And here is R3 and D3. And to describe the multiplexer here, you can use only, because this is 2 to 1, so you can use if SEL R3 equal to 1, so R3 is equal to C in this case, else R3 should be equal to E in this case. Should be done for R3. R4 should be the same because it is a 2 to 1 multiplexer. So you can have R4. And you have R4 here. And of course, this is R4. This is SEL R4. If 1, so we have D. And if 0, we have add 3. So this should be D, and this should be ADD3. Should be done for this. Now we define the multiplier, adder 1, adder 2, adder 3. Multiplier is, yeah, we have the multiplexer here, so we can use the always block or behavioral modeling to model that. Always add. So look at the input. So how many inputs that we can have here? We can have R4, we can have what is this, R3, R1, and R2. So we have all of the possibilities here. Multiplier, we have R1, R2, R4, R1, R3. Yes, so we have R1, R2, we have R3, we have R4, we have SEL M1, and we have SEL M2 for the sensitivity list. So we can use case statement because if we have 4 input like this, yeah, 2 here, 2 here, so we can have 4 possibilities. So we can use case statement. So case, in this case, we have 2 signal SEL M1, so we can use concatenation SEL M1 and SEL M2, right? Such that we can have, for example, if this signal are 0 0, so what is the operation that we want to perform? Okay, if 0 0 means that this line, which is R3, multiplied by R2. So the output MUL is R3 multiplied by R2. If zero one, the output must be R3 multiplied by, if 01 multiplied by R1, R3, R1. If 10, the output must be, if 1 must be R4, so R4 multiplied by R1, right? 10, R1. 1 and 0 are 2, right? 1, 0 is R2. And if the last one, if 1, 1, the output must be R4 multiplied by R1. Okay, so that will be the multiplier. Now what about the adder here? And observe this. Now we describe this. This is the sequential circuit. The multiplier is the sequential circuit. So you can see that I will use the blocking assignment, right? Adder number 1, again, use the behavioral modeling. So we have the R1, R2, and we have R3. So R1, R2, R3. And we only have this option. So we can use if-else statement. If SEL A equal to 1. So the output is must be equal to, if equal to 1 must be this R1 plus R2, or if SELA equal to 0, so else must be again R1 plus R3. Done. And we can have adder number number 2, right? Use always block. We have R1 and R3 only, and this is easy. The output is ADD2 equal to R1 plus R3, and we have another one. Yeah, use different always block because this is add different blocks. Yeah, we want to execute this in parallel. So adder 3, we have R3 plus R4, R3 and R4 for the sensitivity list. So add 3 must be R3 plus R4, then finish for our program. right? So these are the description of this data path, right? So you can see that the process of translating or modeling this is actually straightforward, where we can describe one block or block by block, starting with art1, go to art2, art3, art4, and here, and describe all the connection. And we can see that, yeah, by using the language, yeah, the Verilog HDL, the process of uh, creating the circuit is a lot easier as compared to if you design this using a schematic drawing, right? So that is the advantage of the Verilog or HDL. So now we need to save this and try to synthesize and see whether we have any syntax error or not. If we have, then we need to check whether what the error it is. So yes, we have the error and 10 errors, and let's look at the error and try to learn from this. So can reserve multiple constant driver for net R3 at DU R3 bit number 7. So look at this. When we click this, it will surely bring you to the one that, yeah, to the error that you have, yeah. So in this case, the error is here. So because this should be R4, right? That is the problem with the copy and paste for the program. So we might miss certain label, right? Just like this, we should have R4 here, but because we copy from this, it's still R3, so this is wrong. So that is why we have this error. So let's see again. All right, everything is good. We don't have any error, but we have one another warning, and we should look at this warning. A is read inside always construct, but isn't in the always construct. Yeah, maybe we forgot to to add this in the sensitivity list, right? But it is not a problem actually. It can be automatically insert by the Verilog compiler, but to make it clean, to make our code clean, so we need to have all of this such that we can to make sure that the result, the output later on is correct, right? So we need to make sure that everything that we have, we need to uh, put it correctly. Okay, so we don't have any error, and one warning is okay. This warning is not about the design, but about the license. So that is how we create this to represent this. And we are now at 450, so we don't have time to for the CU. So maybe next week we will continue on this. Now we want to create the CU, and maybe you can try to do it on your own. Try to create the DU based on this CS table, because to create the CU, you need to have this CS table, right? And the CU will be based on this the circuit just now will be based on this circuit, yeah, and the output here is will be based on the CS table here, right?